Good afternoon, everyone. Today we are going to be discussing Design for Automated Assembly, abbreviated as DFAA. The goal is to explore how we can design products with the intent of simplifying and optimizing their assembly through automated systems. This lecture will combine theoretical models, design principles, and real-world applications to help you as a student understand how to develop cost-effective, automation-friendly product designs. We'll not only examine modeling equations, but also interpret what they imply for engineering practice. Throughout, I will highlight several different decisions in the design phase that directly influence the cost and reliability of automation. So, to start off with the introduction, let's talk about why automated assembly is such a critical engineering consideration in the first place. Automation significantly reduces manual labor and the variability that is associated with human operators. It enables rapid, high-volume production and ensures repeatable quality. It also lowers the long-term operational costs. However, automation can only be successful if we design our parts and assemblies to be compatible with automation equipment. That's where DFAA comes in and is really important. Engineering components and assemblies with automation constraints, capabilities, and cost structures in mind. So think about your last group project that involved some kind of assembly. Did you design it assuming that it would be hand-assembled or automatically assembled? Did you calculate the manual handling and insertion times? Thinking about that project, imagine what design changes would be necessary to make it machine assembled. Could you simplify the geometry? Could you add different alignment features? Could you eliminate fasteners entirely? All of these kinds of design considerations must be brought to the forefront when considering automation design. However, these principles are very similar to those described in design for manual assembly, but the designer must consider that a robot gripper or a robot tooling is performing the tasks instead of a human. Let's go through some of the key challenges that are associated with automated assembly. The first is part handling. Asymmetrical or fragile or thin parts can be very difficult to orient, insert, or pick up automatically. Gravity, surface friction, and part compliance can interfere with pick-and-place systems. The second is defect sensitivity. Systems like indexing machines will halt entirely if one workhead fails, so even small defects can result in pretty significant downtime. The third is the demand for consistently high part quality. Automated systems don't easily accommodate variation very well. And finally, automation systems come with pretty significant capital cost, particularly for feeders, robots, and specialized sensors. So that's actually one of the most important things to consider when you are considering between manual and automated assembly. Your automated assembly is going to come with a very, very high, like a much higher upfront capital cost because you have to purchase expensive robotic equipment and all of the different technology that goes into implementing your automated system. However, in theory and in practice, it's supposed to ideally save you money as a manufacturer in the long run, as it can produce parts much faster and reduce the need for manual labor. So there's that trade-off there between automated and assembly, but you need to do those calculations up front, which we'll get into later. A different and separate, deeper issue is the interaction between part design and machine behavior. Parts that have rough finishes or inconsistent tolerances can potentially jam feeders or exceed robot grip tolerances. This can cascade into pretty significant downtime. For example, even a half a part variation across thousands of units can introduce thousands of dollars in delay or scrap every day. This means that DFAA isn't just about part geometry, it's not about part symmetry, it's about controlling the variation across suppliers, batches, and storage environments all within your manufacturing environment. There are two main classes of automatic assembly machines. The first are indexing machines. These operate synchronously, so every station moves together, and if one stops, they all stop. This architecture is fast and simple, but it's very vulnerable to disruptions. It's common for small part counts, and all of the processes must operate with a high reliability to prevent a total system stoppage. On the other side, you have free transfer systems. These operate asynchronously, so they have independent stations that are separated by buffers. These are more robust, fault-tolerant, and scalable, especially for large and complex assemblies. These allow for more design flexibility and fault tolerance across stations. So let's think about their real-world use. Indexing machines are common for small repetitive products, including pen assemblies, electrical connectors, anything where the failure rate is really low and the geometry is standardized. Free transfer systems are preferred for automotive assemblies, consumer electronics, and flexible production lines. A key consideration for the different architectures is fault tolerance. With indexing systems, your design needs near zero probability of jamming or rejection. With free transfer, you can design stations to rework or reject parts locally. This enables more complex products with imperfect part streams. Let's move into a cost modeling example. So the first thing to account for when you're doing a cost model is the equipment downtime, which can be represented by the equation below. In this equation, M is the fraction of defects that actually stop or fault the machine. X is the defect rate. Capital N is the number of assemblies. Capital T is the time it takes to clear the fault. Lowercase t is the cycle time, and N is the number of stations. This model is nonlinear. It tells us either as the number of stations increases or as the defect rate increases, the downtime is going to grow disproportionately to those values. This becomes very critical in high-speed operations. Let's look at an example. If your cycle time is 2 seconds and you run 30,000 parts a day, then a single 10-minute fault is going to cost 300 units. When you multiply this by number of lines, staff, power, and scrap cost, you can very easily see how that downtime is going to translate directly into dollars. So redesigning a feature that can prevent that occasional misalignment, prevent that fault from happening. Let's say you add a bevel, you want to reduce the part friction. This can end up being more economical than tuning out the defect through a final inspection. Okay, so building on that, the total cost model captures 3 types of cost: the processing time, the part handling time, and the quality loss, which is represented by the CFT equation below. Your A sub I is the cost of inserting and feeding the part, which we're going to get into later. And B is the cost penalty per unit defect rate. Okay, so let's look at a live example. If we can assume that my live example. Let's assume that your machine cost is $60 per hour. Your cycle time is 1.5 seconds, which is 0.00417 hours when you do the conversion. Your defect rate is 2%, which makes X equal to 0.02. Let's say you have 1,000 assemblies. You did some time studies and found out that your average fault clearance time is 2 minutes, which is 0.033 hours when you do the conversion. Let's say you have 6 stations and that your M is 0.7. And what I mean when I say that your M is 0.7 means your fault tolerance. So 70% of your defects are going to throw a fault in the cell. And then let's say that you previously calculated your insertion and handling cost to be $1.20. Again, we'll get into that in just a second. And that your B value is going to end up being $100. When you plug in these numbers into the total CFT equation, you get $43.65 as your processing cost, and then you add in your $1.20 for the handling and insertion, and you add in your reject rate cost of $100, and your total cost for that particular unit is, let's say it's $144.85. So let's talk about an example where you as a design engineer would have to make a trade-off decision. So let's say that we can reduce the defects to 1%, but in doing so, that will increase the part cost to, let's say, 10 cents. This is going to lower the B value, or I'm sorry, increase the B value from 100 to 200. So it's going to double that quality term, but in turn, we're going to avoid more tool downtime. We're going to fault less, we're going to create less time that we're spending with the tool down. So all in all, this model helps us simulate different quality scenarios. So at a low X, so a low reject rate, you're going to be producing better parts with better quality, but your B value and that cost is going to grow. However, your total C of M is going to shrink due to less downtime. And then on the flip side, at a high X, so you're making worse parts, your CM is going to exponentially increase due to faults in the cell, due to stoppages, and due to that downtime. So there is a sweet spot of what that X value is where the total cost is going to be minimized. So as a design engineer, it is important for you to find out what that X value, so what should your equipment be faulting at, or what are you going to allow in terms of number of faults, what that fault tolerance is going to be in order to find that sweet spot and find the maximum amount of parts you can produce with the best quality. So this equation is not just an academic equation. It's going to directly inform your sourcing decisions, your tolerance budgeting, and your overall production readiness. Okay, now let's talk about feeding and orientation considerations and how those impact the cost model. So the feeding cost equation is given by the following C sub f. F of r is a variable that is the required feed rate, and F of m is the maximum feed rate that the feeder is capable of. Your C of r value is a relative cost multiplier that depends on your part geometry and your symmetry. This equation implies that as your F of r value increases, your feeder cost drops only up to a certain point. Once F of r exceeds that F of m, the feeder can no longer keep up. So this is influenced by a couple factors. The first factor is your part geometry. So length, symmetry, chamfers, nesting, tangling, all of these things are going to directly impact your C of r value. Some other things include the orienting efficiency, as well as any additional difficulties coming from the part, like if the part is sticky, if it's fragile, if it has overlap, those types of things. Even a seemingly minor design change, such as adding a flat surface or reducing the surface friction, this can move a part from the difficult classification to the easy classification in terms of easy to feed or difficult to feed. Orientation problems often drive the need for expensive vision systems or manual labor. So feeding efficiency is tightly tied to geometric simplicity. And from the textbook, a design tip is that symmetric parts are going to significantly reduce feeder costs and orientation complexity. As you can see from the photo example, these parts that are overlapping are going to feed into the part in a much more difficult manner, as the parts that have been designed with that ledge to not overlap one another, so they'll more easily feed. And lastly, we have insertion cost modeling. So insertion has its own cost modeling equation that's represented by C of I. Your WC is a workhead complexity factor. This workhead complexity is going to increase with things like part stiffness, resistance, or the need for alignment or force control. Things that have a high WC, for example, would be inserting a small pin into a tightly toleranced hole that has a high WC. Things that have a low WC would be just directly dropping a screw into a pocket that's relatively low. Most robotic grippers handle Z-axis insertions really well, but struggle with lateral misalignment. So that's something to take into when you're designing the part, is having as many of those Z-axis alignments as possible. Common design fixes to make a part more easily insertable could be having tapered lead-ins, spring-loaded guides, or even ultrasonic sensors that help verify the fit. These operations are going to ultimately raise the capital cost, but improve the process reliability. A thoughtful insertion plan that's based on both geometry and allowable force can prevent hundreds of failures per shift. These insertion tables come from the textbook, so you can use your part geometry and your tolerances, and actually the tables will guide you to help figure out what your WC factor that you need to use in your cost equation should be. Okay, so to summarize everything from the cost model, we looked at how machine architecture, part design, and mathematical modeling all influence assembly cost and feasibility, but what's more important is how these interact. Example, a part that is cheap to produce but expensive to feed might not be worth it. And conversely, a higher cost part that simplifies insertion and orientation might end up justifying its expense. So as a design engineer, your responsibility is to always think holistically. For example, does a 2-second cycle time justify the complexity of feeding a non-symmetric part? Could adding a 3-cent feature ultimately save $2 in fixture wear or reduce fault rates by 40%? These questions are really at the heart of design for automation. With that in mind, let's go through some key design guidelines for DFAA. The first is to minimize the part count. It simplifies handling and reduces opportunities for failure. Secondly, to make these parts self-aligning using things such as chamfers, tapers, or symmetry. These features are going to help guide the part into place even if there's a slight misalignment. Third, avoid parts that tangle, nest, or require rotation during assembly. These are going to significantly increase your feeder complexity. Fourth is to favor Z-axis insertion. This is going to align with most robotic arms, most robotic grippers, and ultimately simplify your fixture design. Fifth is to use trays or pallets for consistent part orientation. Standardizing the presentation of the part is going to reduce the need for complex orientation mechanisms. You want your robot arm to very easily be able to move ideally up and down in your Z direction and have that be the only movement required. Moves down, picks up the part, moves again, and that's it, instead of orienting and twisting and all of that kind of stuff. Lastly, designing parts to rest stably on flat surfaces. Robots need those consistent pickup points so that they don't end up dropping the part. You should always review part proposals with the following questions in mind. Can this part be fed reliably? Can it be inserted with simple tooling? And could 2 parts be combined into one? Are orientation or compliance challenges likely to add cost? These are all very important automated assembly manufacturing questions to ask yourself at the beginning of the design phase and to really pinpoint the difference between manual assembly as an automated assembly and the cost trade-off and if it's actually going to be beneficial to your product. So, to summarize, automation rewards good design. Use cost models to strike a balance between your part quality and downtime. Design parts for easy feeding and insertion. Prefer symmetry, simplicity, and a Z-axis layout. Use feeders and robots that match your part presentation method. And above all, think systematically. Your assembly cost is not just the sum of your parts, It is the interaction between parts, it's your equipment, and it's also your end product quality. These are the references that were used to put this presentation together. Thank you very much for your time.